Hello, this is John Miares, and as far as I can tell, this will be the last lecture video we are going to have this year. While there is a chance that I may make some more videos that are specific to review for the final exam, this lecture here is the end of the lecture videos. In the last video, we reviewed systems of equations and discussed strategies for solving systems of equations with two equations and two unknowns, with a focus on three different methods. A graphical method, where we looked at the intersections of points in graphs. A substitution method, where we isolated one variable in one of the equations, then substituted an expression to represent it in the other equation. And the elimination method, which focused on combining equations with each other in order to cancel out certain variables and isolate others. Once we expand our focus to more than two variables, the graphical method is no longer feasible, and both the substitution and elimination method become somewhat tedious. In this lesson, we are going to focus on one alternate strategy that uses matrices to represent the coefficients and answers to the systems of equations. Then we'll look at ways that the technology can be used to simplify what will become a variation on the elimination method. Now, please note, the strategy promoted in this section is not my preferred way of solving systems of equations. This process has very few relevant applications outside of this process. However, since this material does show up in one question on the final exam, I do feel obligated to cover it before the end of the course. Also, just like with section 10.1, content from this section is only going to be included on the final exam and not part of Quest 6. Suppose you are asked to solve a larger system of equations, such as the one that is shown here on the screen. We have three variables to solve for, x, y, and z, and three equations that connect them to each other. There are several different strategies that can be employed and you may have been exposed to in previous courses, which might have included variations on the substitution method or the elimination/linear combination methods taught in section 10.1. There are also several other strategies involving converting the system of equations or parts of it into these things called matrices, which can be manipulated in order to obtain the desired solution. We are going to be exploring one of those strategies in this course, but by no means should this strategy be considered the only way to solve them, nor should it be considered the best or the easiest way to solve these systems of equations. Although, admittedly, the process goes pretty quickly when you use a graphing calculator. Before we can get into how to go about solving the system of equations using matrices, we need to define what is a matrix, or what are matrices, where matrices is the plural of matrix. A matrix is an array of numbers that is set up in a rectangular table, normally enclosed in brackets and labeled with a capital letter such as A or B or C or D, like those you see here on the screen. The dimensions of a matrix are defined by the number of rows and the number of columns in the matrix. So when I want to discuss the dimensions of a matrix, what we're going to do is count how many rows and how many columns each table or matrix or array has. As a reminder, rows go horizontally and columns go vertically. If you need a better visual to help you remember which ones are rows and which ones are columns, you can think of it this way. Columns hold up buildings, so those are going to be vertical. Farmers plant crops in rows, so those are going to be horizontal. Based on that, what can you say that the dimension of each matrix is going to be? Why don't you pause this video and see if we can figure that out? All right, let's see how you did. Matrix A has 3 rows and 2 columns. So we're going to say that matrix A is a 3 by 2 matrix. Matrix B has 3 rows and 3 columns, so its dimensions are 3 by 3. We will also refer to matrix B as a square matrix because the number of rows and columns will be equal to each other, and the table looks more like a square. Matrix C is going to be a 2 by 3 matrix. It has 2 rows and 3 columns. Matrix D is going to be a 4 by 1 matrix. Sometimes refer to matrices like matrix D as a column matrix because, well, it just has 1 column. Interestingly enough, column matrices are also sometimes called vectors, but we're not going to get into that here. Now, for the lesson we are covering here, we are going to introduce the concept of an augmented matrix. An augmented matrix is one that starts out as a square matrix containing all the coefficients of all the variables from a system of equations, but then an additional column is augmented on the right side that contains the constants that show up after each equal sign in the system of equations. An example of this is going to be shown here. Suppose I have this particular system of equations. The first step we're going to need to do to solve this system is have the coefficients listed in each row and then have the answer on the right-hand side of the equal sign over this little vertical bar over here. And this is how we're calling this an augmented matrix. So I have the 3 by 3 square matrix that has my coefficients in it, and then I'm augmenting a column matrix on the right-hand side that contains the values that are on the equal sign, or on the other side of the equal sign. So my first equation, 2x plus 1y minus 3z equals 5, will translate here as a 2, a 1, a minus 3, and then a 5 on the other side of the bar. Similarly, with the middle equation being x minus 2y plus 4z equals 3, I have 1, -2, 4, and then 3 on the other side. Finally, in the third row, I have 3x minus y minus z equals 1. The coefficients for each variable are going to be 3, -1, and 1, and my answer comes out to be a 6 on the far end. Now, if this system had one variable missing, like if this was just 3x minus z equals 6, so there was no y term, I would put a 0 as the placeholder here for that coefficient. The strategy for solving this system of equations that we're going to introduce here is called Gaussian elimination, and it is named after a German mathematician and physicist by the name of Carl Friedrich Gauss, who did most of his work in the early 19th century. This method is sometimes also called the row reduction method, and the idea is that we're going to use something called elementary row operations and apply them to the augmented matrix in order to eliminate the variables and solve the system of equations, in much the same way that synthetic division can be used when attempting to do algebraic long division. The goal is to convert the equation into something called row echelon form, or REF for short. Once it is in this form, the solution to the systems is pretty quickly attained. So what does it mean to be in row echelon form? A matrix is said to be in row echelon form if it satisfies the following conditions. The first non-zero number in each row, reading from left to right, is 1. This is called the lead entry. Second, the lead entry in each row is to the right of the leading entry of the row immediately above it. And third, all rows consisting entirely of zeros are at the bottom of the matrix. So let's try putting this into plain English. We'll start with our augmented matrix here. And we're going to do a lot of swapping and combining and manipulating between the rows until we get something where you're going to see ones along the main diagonal of the matrix here, and then zeros below all those ones. Any other non-zero number is going to be above the main diagonal. Now, you could be staring at this and wondering why we care about this anyway. Well, our original augmented matrix represented the coefficients and the answers for our original system of equations. 2x plus y minus 3z equals 5, x minus 2y plus 4z equals 3, 3x minus y minus z equals 6. This new augmented matrix will give us an updated system of equations that is algebraically equivalent to what we started with, but will be much easier to solve. The top row with the 1, the 3, the minus 7, and the 2 is going to translate to this first equation, x plus 3y minus 7z equals 2. The second row of the matrix with the 0, the 1, the negative 11 fifths, and the negative 1/5 translates to y minus 11 fifths z equals 1/5. And this bottom row, 0, 0, 1, 1, simply becomes z equals 1. Now, knowing that z equals 1, we can substitute that into the middle equation to get y minus 11 fifths times 1 equals negative 1/5. If I now add 11 fifths to the other side, you're going to get y equals 10 fifths, which reduces to just 2. Now that you know that z equals 1 and y equals 2, we can substitute both of those values into the top equation, which was x plus 3y minus 7z equals 2. So it becomes x plus 3 times 2 minus 7 times 1 equals 2. Simplifying that a bit will get you x plus 6 minus 7 equals 2, or when you combine the 6 minus 7, you get x minus 1 equals 2. Adding 1 to the other side will get you x equals 3. So my final answer to this system here, I've got x equals 3, I've got y equals 2, and I've got z equals 1. So hopefully you can see that if I am able to take this original matrix and manipulate it to get it into this row echelon form where I've got ones on this main diagonal, zeros down below the diagonal, that this solving of the system is not going to be so bad. Now, a variation on this is something called reduced row echelon form. Reduced row echelon form takes this a few steps further. A matrix is considered to be in reduced row echelon form if it is not only first in row echelon form, but it also satisfies the condition that every number both above it and below each leading entry is a 0. In short, what that means is that after I get to this point where I've got ones along the main diagonal here, we want to see if we can take this further to get it to a point where I have ones along the main diagonal, and then I've got all these zeros below it, and I've got now all zeros above it. So the only non-zero numbers are going to be the ones in the main diagonal and these numbers on the right-hand side of the bar here. If we can get it somehow to this point, then the answers to the system of equations are going to come about even faster. This is going to translate into x equals 3, y equals 2, and z equals 1. So really getting the solution into reduced row echelon form right away is the ideal situation because we can get the solutions to the system directly. But better yet, our calculators can do all of this work for us from taking our original augmented matrix and converting it into either row echelon form or reduced row echelon form. Now, I'll say this right now. The processes associated with doing Gaussian elimination and converting matrices into either row echelon form or reduced row echelon form are long, tedious, and confusing. Personally, and I mentioned this earlier, I have no use for doing Gaussian elimination, at least by hand. It is not anything that I have ever found that I have ever had to do in my entire life of studying and working with mathematics. And remember, not only have I been teaching for a long time, I have worked as a professional statistician where I do math all day long. If I don't use this in the workplace, I have no intention of showing you how to do this Gaussian elimination by hand. So what we're going to do is focus on how the graphing calculator can do many of these processes for us so that you don't have to do them by hand. Of course, if you are interested in seeing the processes work in detail, I do show an example of how to do this in the notes packet. And I've marked it off in the notes packet with a section that says gobbledygook starts here and gobbledygook ends here. And there may also be other videos out on the internet, maybe through Khan Academy, maybe on YouTube, that can help you work through it the long way. Long story short, I will never, ever ask you to do one of these computations by hand. You will, however, need to understand how these processes work on the calculator and how to interpret the results of what the calculator gives you when it does it. So, given all of this, let's see how we can do this process on the calculator and see what it all means. The first thing we're going to need to do is go to the matrix button on the calculator, which you can get to by pressing second function and then this x to the minus 1 key where it says matrix right above it. Next, I'm going to click the right arrow to get to the edit options, and then I'm going to select one of the 10 matrices that are listed as being available, A through J. On the TI, the matrices are enclosed by brackets like A or B, like I can see here. For our purposes, I'm just going to use matrix A. When we open up the matrix, we need to set the dimensions. What I have here is a 3x3 system of equations, so the augmented matrix is going to have 3 rows and 4 columns. So I'm going to enter that I have 3 rows and I have 4 columns. So now that I have the dimensions in here set up, what I see is that the calculator has set various placeholders for me in here for me to enter the numbers from my augmented matrix. Now, the other thing I'll mention is that when I go to type in the numbers, I'll start on the top left, and if I hit enter, it's going to go across the rows. So the original matrix we were working with started with a 2, 1, -3, 5, and it's going to go to my second row. 1, -2, 4, and 3. And then my third row, I've got 3, -1, -1, and 6. Once the data are entered, I can return to the home screen by hitting second function quit, which again, second function mode, we see the little quit sign there in yellow. In order to have the calculator perform the desired operations on this matrix and get it into row echelon form, I want to return to the matrix menu. So I'm going to hit again, second function matrix. And I want to press the right arrow to get to the math options. And if I scroll down far enough, I have this option A, which says ref, and option B, which says RREF. We are going to look at both cases here, but I want to start with REF first. So I'm going to select this option. I'm going to say it says REF, and now I need to choose what matrix I want to convert into row echelon form. To pick that matrix, I'm going to hit second function matrix again, and then under names, I will select matrix A. I can close the parentheses. For this, you don't have to close the parentheses because it will do it for you anyway. After I press enter, I have this. So in the top row, I see 1, -0.33333 repeating. Those decimals make it look a little bit ugly. But what I'm going to do here to make this look a little bit cleaner is I can hit the math button and choose the frac option, and then that will take this answer with all these decimals in it and turn it into something with fractions. So now what I can see here on my top row, I've got 1, -1/3, -1/3, 2. In the middle row, I've got 0, 1, -13/5, and -3/5. On the bottom row, I've got 0, 0, 1, 1. So we can take these answers that we have here and use them to set up an updated system of equations that can be solved fairly readily, like I showed on an earlier slide. Now, we could also jump ahead and use the RREF option in the matrix menu. I'll show that here. Let's hit second function matrix. I'm going to go right arrow over to math, and I'm going to scroll down. So it says RREF, which is option B. I'll select that. And again, I need to tell it what matrix I want to convert into reduced row echelon form, or RREF form. I'll hit second function matrix and select matrix A. I'll close my parentheses and I'll hit enter. And now we have this where I can get my answer coming through pretty quickly. That 1003 means x equals 3. 0102 is going to be y equals 2. And 0011 becomes z equals 1. Now, sometimes you might also get fractions involved in this process, but then again, I could just hit math frac, and that will take whatever answers that I have in ugly decimal form and try to convert them into fractions. Here's an example that perhaps you can try on your own. Take the system of equations here and convert it into an augmented matrix and enter it into your calculator. Then try to use the REF and RREF features on the calculator's matrix menu to convert this into row echelon form and reduced row echelon form. From there, we're going to try to solve the system of equations. For reference, while you're trying this, I'll show you the screenshots of the steps that you're going to need to do on your calculator in order to get this problem solved. So our augmented matrix is going to be a 3 by 4 matrix, and it's going to look like this once I've entered it into matrix A on my calculator. The top row is going to have entries 1, -1, 2, and -3 to represent the equation 1x minus 1y plus 2z equals -3. The second row corresponds to the second equation, 1x plus 2y plus 3z equals 4. And the third row matches up with the third equation, 2x plus 1y plus 1z equals -3. Using the REF option on this matrix should give you something that looks like this, although you may have needed to hit the math frac option on your calculator to see all the terms in this matrix reduced to simplified fractional form. This matrix now translates into the updated system x plus 1/2 y plus 1/2 z equals -3/2. The second equation, y plus 5/3 z equals 11/3, and the third equation, z equals 1. Now we could solve this equation from here, but instead I'm going to go straight to the RREF option on the calculator, the reduced row echelon form, which will look like this, which again has all ones along this main diagonal here, and zeros everywhere else above and below the matrix except in this last column. The last column is going to translate into the values we're trying to solve for, which is going to make our final solution equal to x equals -3, y equals 2, and z equals 1. Here's another one that you can try on your own. This one has 4 equations and 4 unknowns. So our augmented matrix this time must be a 4 by 5 matrix. Go ahead and pause this video one more time to see if you can work this one through on your own. So our augmented matrix is going to look something like this. So I'm going to enter it into the calculator under matrix A, which will be a 4 by 5 matrix as shown here. If we were to do just the REF option on the calculator, we'd get something that looks like this, which is going to translate into the system w plus x plus y plus z equals 2, 2x minus 1/2 y equals 0, y equals 4, and z equals -1. Of course, we could go straight to the RREF option to get our solution here, which looks like the following. And we can translate that into a final solution of w equals 1, x equals 2, y equals 4, and z equals -1. So at the end of the day, if the goal is to get the solution to the system of equations, and I'm not going to make you show any work, then you can go straight to finding the reduced row echelon form, or RREF, without having to find the row echelon form, or REF, first, because that will certainly speed up getting your problems completed. We sometimes have a situation, however, where the calculator will not lead us to a solution that is unique. When that happens, we have to take a different approach. Just like with 2 by 2 system of equations, it is possible that you can have a system that doesn't necessarily have one unique solution. You could have one that has no solutions, or even infinitely many solutions. In those situations, when we try to have the augmented matrix converted into row echelon form, we see some bizarre behavior. One possibility is that you have no solutions to the system of equations. If the row echelon form contains a row that represents the equation 0 equals some constant c, where c does not equal 0, then the system will have no solution. Just like with a 2 by 2 system when this situation occurred, we're going to call a system that has no solutions inconsistent. Now, when it was a 2 by 2 system, we could graphically see there were no solutions to the system because the lines that represented the equations were parallel. Well, once we start getting into 3 by 3 or 4 by 4 systems of equations, we're not dealing with lines in a plane anymore. We might be dealing with lines in three-dimensional space, but those don't have to be parallel in order to not intersect with each other. The next alternative is when you have a situation with infinitely many solutions. If all the variables in the row echelon form are not all leading variables, and if the system is not inconsistent, meaning that at least one of the matrix rows contains all zeros, then it will have infinitely many solutions. In this case, the system is called dependent, and we can solve that system by putting the matrix into reduced row echelon form, then express the leading variables in terms of the non-leading variables. Well, a non-leading variable then may take on any real numbers as their values. So a leading variable in a linear system is one that corresponds to the leading entry in row echelon form of the augmented matrix of the system. So admittedly, that in itself is a lot of gobbledygook, so maybe it would be better if we looked at some examples of where this occurred. In a dependent system, or one where there are many possible solutions, the bottom row of the matrix, when you convert it into REF form or RREF form, is all zeros. Let's say our system of equations looks like this. To speed things up, I'm not going to go through the entire process of entering this into the calculator, but I would encourage you to do this one on your own. The augmented matrix is going to look like this, which we can enter into the calculator like so. When we try to put this into row echelon form, or REF form, we get something that looks like this. And the REF form, or reduced row echelon form, is going to look like this. Now, the top row and the middle row will still translate into equations that we think we might be able to do something with, such as x plus 4z equals 10 and y minus 1/2 z equals 7/2. But the bottom line of the augmented matrix basically says 0 equals 0. When this happens, that implies that z can be anything we want it to be, implying that there isn't going to be a unique solution to the system, but rather the values for solutions to x and y will be dependent upon whatever we pick for z. And z can be anything it wants to be. Typically, what we would do when we write out this equation is to solve for each variable in terms of z. So here's the equation: x equals 10 minus 4z, and y equals 7/2 plus 1/2 z. But z can equal anything. So if we said, let's let z equal 1, you're going to get certain answers for x and y. For z equals 1, you'll get x equals 10 minus 4, which is 6. If z equals 1 on the y equation, you have 7 halves plus 1 half is going to be 8 halves, or 4. So one possible solution is going to be 6 for x, y is 4, and z is 1. If we plugged in z equals 0, I'd have 10 minus 0 is 10 for x, 7 halves plus 0 is 7 halves for y, and then z equals 0. So yeah, depending upon what I plug in for z, you're going to get different answers for x and y. And that's okay. But that's why we call this system dependent, because the values of x and y will be dependent upon whatever number we decide to plug in for z. In an inconsistent system, the bottom row is going to have all zeros except in the last column. Let's look at an example of that. Let's say our system of equations is this one right here. Again, it wouldn't hurt for you to pause this video to see what this is going to look like if you were to try plugging this into the calculator yourself and converting it into row echelon form or reduced row echelon form. But I'm not going to insist you do that at the moment. If you are willing to take my word as to what the results of this effort should look like, then we'll be okay moving forward. The augmented matrix will look like this. And if we plug that into matrix A as a 3x4 matrix, it should look something like this. Now, if we ask the calculator to put this into row echelon form, what you're going to get is something that looks like this matrix here in the middle. The first clue that you have a problem is that I don't have all ones along this main diagonal. The bottom row has 3 zeros and then a 1. Translating that back to a system of equations looks like this, with 1x plus 2/3 y minus z equals 10/3, then y equals 2, then 0 equals 1. That 0 equals 1 on the bottom row essentially means that there isn't going to be any way we're going to find a solution for z that will fit the system. If we went to the reduced row echelon form right away, we'd have something that looks like this, which will translate into the equations x minus z equals 0, y equals 0, and 0 equals 1, which again, that bottom row with the 0 equals 1 in it means that the system is going to have no solutions. Before we close out this presentation, I want to look at one word problem involving a larger system of equations and see how we can use matrix methods to solve it. Here we go. Len and Will own a candy store in the town of Seal Cove. For an upcoming promotion, they need to sell their excess fudge. They decide to package the fudge in 3 different ways according to the following proportions. They're going to sell big boxes of fudge, which will contain 8 ounces of chocolate fudge, 5 ounces of peanut butter fudge, and 3 ounces of maple walnut fudge. A medium box will contain 6 ounces of chocolate fudge, 3 ounces of peanut butter fudge, and 3 ounces of maple walnut fudge. A small box will have 5 ounces of chocolate fudge, 2 ounces of peanut butter fudge, and 1 ounce of maple walnut fudge. If 96 ounces of chocolate fudge, 51 ounces of peanut butter fudge, and 37 ounces of maple walnut fudge are available, how many of each size package may be produced? Set up and solve a system of equations using matrix methods. Let x equal the number of big boxes, y equal the number of medium boxes, and z equal the number of small boxes. All right, there's a lot of information to digest here, but the solution strategy is going to be similar to what we did when we were solving 2x2 equations. We first have to determine what it is we are trying to solve for. Then work on setting up a system of equations that will get us towards that solution. Once we have the system, we can set up an augmented matrix to represent the system, plug it into our calculator, have the calculator compute the reduced row echelon form, then get an answer, or not, and interpret the solution that the calculator gives us in the context of the word problem. So what we're asked here is to find the number of boxes of each size that can be produced with the quantities of fudge we have on hand. We're even told that we should have X be the number of big boxes, Y be the number of medium boxes, and Z be the number of small boxes produced. Looking at the different types of fudge available, we know that for chocolate fudge, big boxes contain 8 ounces, medium boxes contain 6 ounces, and small boxes contain 5 ounces. And we have 96 ounces of chocolate fudge altogether. This can translate into the equation 8x plus 6y plus 5z equals 96. That's essentially saying I've got 8 ounces of chocolate fudge in a big box times X amount of big boxes, plus 6 ounces of chocolate fudge in a medium-sized box times Y number of medium boxes, plus 5 ounces of chocolate fudge in a small box times Z number of small boxes will add up to the 96 ounces of chocolate fudge that we have. We can do the same thing with the peanut butter fudge. We know that big boxes use 5 ounces, medium boxes use 3 ounces, and small boxes use 2, and we have a total of 51 ounces of peanut butter fudge total. This is going to translate to the equation 5x plus 3y plus 2z equals 51. Again, the coefficients represent how much peanut butter fudge is in each size box, and X, Y, and Z represent the different size boxes. So fudge per box times number of boxes plus fudge per box times number of boxes plus fudge per box times number of boxes adds up to the total amount of peanut butter fudge that we have. Finally, we have the maple walnut fudge, where a big box and a medium box both contain 3 ounces of maple walnut fudge, but the small box only has 1 ounce, and we have 37 ounces of maple walnut fudge total available. Putting that together into one equation gives us 3x plus 3y plus 1z equals 37. Now we have 3 equations and 3 unknowns. See if you can work this one through on your own on your calculator, and then we will check the solution on the next slide. So here is our system of 3 equations with 3 unknowns. The first equation is based on the amount of chocolate fudge we have, 8x plus 6y plus 5z equals 96. The second equation is based on the peanut butter fudge, 5x plus 3y plus 1z equals 51. And the third equation is tied to the maple walnut fudge, 3x plus 3y plus 1z equals 37. We can turn this into an augmented matrix, which looks like this, then enter it into our calculators as matrix A, which will be a 3 by 4 matrix. We can either go with the row echelon form, or REF for matrix A, which looks like this, and will translate into this system of equations here, where we will still have to do some work in order to get the final solution. Or we could dive right into the reduced row echelon form, or RREF, which will get us straight to the solution: x equals 5, y equals 6, and z equals 4. Once we get this solution algebraically, we will need to go back and answer the question in the context of the word problem. Essentially, we need to make sure we're answering the question that we were asked. X stood for the number of large boxes we were going to make. Y stood for the number of medium boxes. Z stood for the number of small boxes. Knowing this, we can answer this question by saying Len and Will can make 5 large boxes, 6 medium boxes, and 4 small boxes of mixed fudge from their available supplies. Before I close out this presentation, what I do want to take the time to do is show you how we can use one of the programs that I had posted to D2L that you should have installed on your calculator that can be used to solve these systems of equations without having to remember a lot of these commands. The program itself looks like it's called SYSOFN, which if I hit the program button, it's going to be near the bottom and spelled SYSOFEQN. And it's short for Systems of Equations. When I hit enter, and then I hit enter to start the program, it tells me nicely what the program does. This program can be used to solve a system of equations. I'll hit enter. It's going to ask me how many variables we have. Let's say we were doing the example with Len and Will and their fudge shop. This one had 3 equations and 3 unknowns, so I'm going to say the number of variables is 3. Equation number 1. This is where we're going to enter the coefficients for that first equation. This is where we said I've got 8 ounces of chocolate fudge in a big box, 6 ounces of chocolate fudge in a medium box, 5 ounces of chocolate in a small box, and it says answer, that's going to equal 96. And basically what the calculator is doing as I'm taking these numbers is it's entering them into the matrices for you so that you don't have to remember which way they go. Then for equation number 2, let's say that this was going to be for the peanut butter fudge. We had 5 ounces in a large box, 3 ounces in a medium box, 2 ounces in a small box, for a total of 51 ounces of peanut butter fudge. And in my third equation, I've got 3 ounces of maple walnut fudge in a big box, 3 ounces in a medium box, and 1 ounce in a small box, for a total of 37 ounces that we have on hand. So now when I hit enter, it's going to tell me the solution right away. The solution is going to be 5, 6, 4, which is what I had before. X equals 5, Y equals 6, and Z equals 4. What I want to do now is show you what would happen in this program if I had either a dependent system or an inconsistent system. Let's take a look at what happens with the dependent system that I presented earlier in the notes. I'm going to hit enter to start the program again. It tells me this program can solve a system of equations. I'm going to hit number of variables is 3. And I'm going to do the same thing. I'm going to say the coefficients here, it was 1x minus 2y, so I'll type it in as a negative 2, plus 5z equals 3. Then I'll say negative 2x plus 6y minus 11z, so I'll say that's negative 11, equals 1. And then I have 3x and negative 16y and 20z equals negative 26. So now I've put this in here. What it first says is that there is no one solution. But what it will say is maybe we need to look at the reduced row echelon form. So if I hit enter on this, it's going to show me what the reduced row echelon form is going to look like. And what I notice here is that I've got 0, 0, 0, 0 on the bottom row. And when I have 0, 0, 0, 0 on the bottom row, that means that this is going to be a dependent system, that I can rewrite this in terms of x in terms of z and y in terms of z, and then say z equals anything. For my last example, I want to look at that one that we did with the inconsistent system. So if I hit enter here, I'm going to start that one up where I have three variables, three unknowns. I'm going to say 3x plus 2y minus 3z equals 10. I've got 1x, negative 1y, negative 1z equals negative 5. Then I have 1x, 4y, negative 1z equals 10. And now when I hit it, it's going to say there is no one solution. And when it says that there is no one solution, it means that possibly there is no solution or possibly there's many solutions. So what it then says, press enter to see the reduced row echelon form. I'll hit enter and I can see right away, again, the dead giveaway that there is going to be a problem, that this is going to be inconsistent with no solution, is that my bottom row has all zeros in it except in the last one. So if it looks like 0x plus 0y plus 0z equals 1, that means truly there is no solution to this system of equations. It will be an inconsistent system. When it's all zeros on the bottom row, that means we're going to have a dependent system, and there's going to be an infinite number of solutions. If this came out with 1, 1, 1 on that main diagonal and then all zeros everywhere else except the last column, then I would have a nice, clean, unique solution. So we've made it to the end of the last lecture presentation that you're going to have to listen to this semester. Congratulations. I hope it feels good to get to this point. Again, the content covered here is not going to be on Quest 6. And realistically, you're only going to see this on one question on the final exam. So as long as your calculators are working, it shouldn't be so bad to get through. Also, again, it is not critical that you ever try to figure out how to do these manipulations to get these augmented matrices into row echelon form or reduced row echelon form by hand. But you should know how to do these problems on your calculator and be able to interpret what the output of the calculator is telling you. I'm hoping that, on the whole, this really isn't that hard a topic to deal with, as my hope was to end the semester with something that wasn't going to be particularly hard or stressful as we prepare for the final exam. We will be discussing these problems in an upcoming ORT session, so go ahead and give these problem challenge problems a try in the next day or so. If you have any questions or concerns, feel free to contact me by email, or you can post your question on the discussion board. Thanks for watching, and we'll see you all soon.